All right, this is our big review and we want to walk through it. At times, I'm going to have you pause and try the problem that you're seeing if you haven't done these already ahead of time. Some of these slides will just be information, but others of them will be a chance for you to practice and then see how you did right afterwards. So this very first slide is just like that. Why don't you go ahead and pause and see if you can answer these 4 questions and say what point there. I'll give you a second. Okay, so the limit exists, but the function is not defined. So we want a place where we have a value that it looks like the function is supposed to equal, but there actually is no dot anywhere along. So A definitely has a limit, but it also has a function value. B does not have a limit. We have a break in the graph there. C, we have a limit. It looks like the function is going to equal this value of L, but there is no value there. So C is the place where the limit exists, but we don't have a function value. The limit exists, but the function value is different. So again, that was what we saw right away. A has a limit. There's a spot where it definitely looks like the function should equal this. That would be the limit, but the function value is actually up here. So A is our answer on that one. The limit does not exist, and again, that would be B. We have that break in the graph. So from the left and the right, there's a disagreement. The function is continuous but not differentiable. So if you look at D, we can trace. I can put my pencil on the paper, trace this the whole time, never had to lift it off. But because of that sharp turn, we're not going to have a derivative right there. So D would be our choice on that one. All right, so hopefully you felt pretty good about that. Calculating limits, why don't you go ahead and pause and see if you can work this out using Lhopitals Rule or something else. So Lhopitals Rule says plug in your value first. So if we put 0 into this, we're going to get 0 over 0. That's what's called an indeterminate form. Doesn't hurt to even say that here, indeterminate form. And then we're going to use Lhopitals. You definitely want to write down that you're doing Lhopitals Rule on this one. So Lhopitals Rule would say take the derivative of the top. That's going to be 6x minus 2. Over the derivative of the bottom, which is going to be 15x squared plus 4. Let's try that limit again. So if I put 0 in now, I'm going to get negative 2 over 4, which is a negative 1/2, and that's our answer. Okay. Now you could get this by factoring or doing some other stuff too, and that's fine. But Lhopitals is a nice tool that works on a lot of different things. So same thing right here. If I were to put pi in here, I'm going to get 0 over pi minus pi, which is 0. That's my indeterminate form. So I'm going to use Lhopitals Rule. And Lhopitals Rule says take the derivative of the top, which would be cosine. Take the derivative of the bottom, which will be 1. And try it again. And now if I do cosine of pi, I get negative 1 over 1, which is negative 1. Okay. So if you get something like that, Lhopitals Rule works nicely. Take the derivative of the top, derivative of the bottom. You're good to go. Definition of continuity. Remember, for something to be continuous, the limit has to exist. The function has to be defined. And those two have to equal each other. So the limit as x approaches c of this function has to equal the function value at that spot. So those are the 3 things you're trying to test for. So why don't you go ahead and pause and see if you can show that this function is continuous and see if you can show that it's differentiable. Okay. So to show that it's continuous, we want to show that the limit as x approaches 2 from the right side would be our top part coming from the right. So that's going to be 2 squared plus 4, which is 8. Our limit as x approaches 2 from the left side will be the bottom part. That's going to be 4 times 2, which is also 8. So therefore, the limit as x approaches 2 is 8. And that equals f of 2. And the reason we know that is because it is defined right there. So therefore, f is continuous at x equal 2. Okay. So we want to show the left-right makes the full limit, show that equals function value, and you got your continuity. Not too bad. So show that it's differentiable. So now we want to show the limit as x approaches 2 from the right of the derivative of f. So that's going to be the derivative of the top part. The derivative of the top part is going to be 2x, so 2 times 2, which will give us 4. And then the limit as x approaches 2 from the left side of our derivative would be the derivative of the bottom part, which is just 4. So we've got a limit of the full derivative is 4, because we have that agreement there. And that's going to equal f prime of 2, which was also 4. So therefore, f is differentiable at x equal 2. So you're trying to take the derivative of the top, derivative of the bottom, see if those match up. That's what we're trying to do on that part. Next, we've got V of t is the volume of a balloon in terms of cubic centimeters after being filled with air. I want you to see if you can figure out what V prime and V double prime would represent and what would their units be. Okay, so what does V prime represent? Well, if V is the volume, then V prime would be the rate that the balloon volume is increasing. Rate that volume is increasing. And that would be, since the volume is cubic centimeters and t is in seconds, it would be cubic centimeters per second. And V double prime then would be the rate that the rate is increasing. All right, so this is the change in our rate, and this would be cubic centimeters per second, or per second squared, however you prefer to write it. All right, so be sure you know what your equation is representing, and then that derivative would take it up to the next notch. Okay. Now we're going to, same situation, but this time V of t is going to represent the actual rate of this. All right, V of t is the rate that the volume of the balloon is changing, and we want to know what these things represent. So go ahead and pause and see if you can figure out. All right, so what does V prime? Well, V of t is the rate that the balloon is changing. Then V prime would be actually the exact same thing V double prime represented up here. It's the rate that the rate is changing. And again, that would be in cubic centimeters per second, or per second squared. Either one of those is fine. What does the integral from 3 to 11 represent? Well, if V of t is the rate, then when you integrate the rate, you get the change in the volume, right? So this would be the change in volume from 3. And since this doesn't tell us, we're just going to write t equal 3 to t equal 11. So from that time period, this would represent how much it changed, how much did it accumulate. Okay. Now this bottom one here says, what does this represent? This would be the average of V of t from 3 to 9, but they said that they're not going to ask you about average value on this test, so this is not something that we need to worry about on ours. All right, so don't panic. If you felt good about that, then you're in good shape. Now this might be the most important page that I would have on my note sheet. If I was going to have anything, I would just make sure that this was there so that I could reference it, because a lot of their questions might come back to something like this. Take a second, see if you can remember how to fill these blanks in. Okay, so if V prime is less, if the derivative is negative, that means our function is decreasing. And if our function derivative is positive, it means our function is increasing. Again, that's something they're going to ask you about for sure. I would make sure that's somewhere close by in case for some reason you forget. Let's do the second derivative. Take a pause and see if you can fill these in. Okay. If the second derivative is negative, that means my first derivative is decreasing and means my function is concave down. If my second derivative is positive, that means my first derivative is increasing and means my function is concave up. Again, this is something I would have close by, just to make sure you are good on it. Okay? You probably will be asked something along those lines for sure. Now this one gives you a graph and asks where is the function value less than the derivative value less than the second derivative value. And then this one says where is the derivative negative and the second derivative negative. See if you can figure out those real quick. Right. And usually when they ask something like this, this value would probably be negative, this value would probably be 0, this value would probably be positive. I'm looking for a point that has a negative that's below the x-axis, negative function value, probably has a horizontal tangent, and is at a point in the graph where it's concave up. And if I look, I see it right there at endpoint B. Okay, B has a function value that's negative, a horizontal tangent line, and is concave up. Okay. Now, where on this graph do I have a negative derivative? Well, that would be anywhere I have a negative slope, so that'd be A and G, and have a negative second derivative, so that means it would be concave down. A is on a concave up part, G is on a concave down part, so I would say G would be our answer there. Okay. This next page is just a reminder of the trig formulas. You would hopefully know sine and cosine really well, but you'd want to have at least these two written. It wouldn't hurt if you have the space to write them all, but I don't think they're going to ask you these two. Would they ask you about this? Maybe. I don't know. But it wouldn't hurt you at all to have that ready to go just in case. So this page right here, just information only. As is this page right here, which is our derivatives of natural logs and things. And this one here is just saying the derivative of natural log is 1 over x. If it's anything more complicated than that, it's going to be 1 over whatever was inside times the derivative of what was inside. Okay? Same thing with e to the x. Derivative of e to the x is e to the x. If it's anything other than x, then you're going to repeat the whole thing, e to whatever it is, times the derivative of what was inside there. Okay? So we're going to pause this. This is the end of part 1, and then part 2 we'll pick up with some derivatives.